Hello everyone, welcome to the second part of Lab 8 on Kruskal-Wallis test. Earlier this week, we used ANOVA to detect statistically significant differences between three or more groups. But as I discussed, ANOVA makes very important assumptions, and one of them is particularly important, which is that of normality. Right? ANOVA, just like other parametric tests, like independent sample tests or pair sample tests, ANOVA makes the assumption that your dependent variable is normally distributed. And often this is not the case, such as earlier in the week when we tested the normality assumption on the income of the General Social Survey the General Social Survey data that we analyzed. And when this assumption is violated, you should not take it lightly, right? Even if your sample is kind of large, if the skew is, quite substantial, if the data is really not normally distributed, then you should really consider using a non-parametric version of a one-way ANOVA. So the non-parametric version of a one-way ANOVA is called the Kruskal-Wallis test. Right? So the Kruskal-Wallis test is a non-parametric method for testing whether three or more samples originated from the same distribution. Meaning, are they from the same distribution or are they statistically significant from each other? So this is an extension of the Whitney U test for two or more groups. As a parametric equivalent to a one-way ANOVA, the Kruskal-Wallis test is often called a one-way ANOVA on ranks. But unlike the ANOVA, this test does not assume a normal distribution. So the null hypothesis of the Kruskal-Wallis test is that there's no difference in the distribution or medians of groups. The alternative hypothesis is that at least one of the groups' distribution or median is different. Assumptions, it assumes that the data is not normally distributed. So only use the Kruskal-Wallis test if your data is not normally distributed. If your data is normally distributed, you should use an ANOVA. The variable of interest or your independent variable should have three or more groups. And the sample size, the smallest sample size that you can have is that of 5. So let's start this discussion with just a toy example, just to see how it is calculated. So let's say that a researcher is interested in the relationship between young people's sleeping habits and their mental well-being. A survey is conducted where participants report their average hours of sleep and their well-being scores. Here, we will analyze the data using the Kruskal-Wallis test. So, here are the groups. You have 3 groups: kids that sleep 8 or more hours, 6 to 8 hours, less than 6 hours, and these are their well-being scores. So, as always, you start with your null hypothesis. The null hypothesis is that there's no difference in the distribution or medians of well-being scores across sleep groups. The alternative hypothesis is at least one sleep group has a different distribution or median of well-being scores compared to the others. So just like the Whitney U test, you start by ranking all your data, right? All your data, right, from the lowest to the highest. So here, 1, 2. And if you have ties between your data, you should just average the rank, right? Such as in this case. So 42 and 42 get 6.5, right? Once you have calculated the ranks, then you want to sum the ranks. You have to divide the rank by group and then sum the ranks by group. So the sum of ranks for 8 hours is 48.5. The sum of ranks for 6 to 8 hours is 43. And less than 6 hours is 32. So you can see that the highest ranked well-being scores are in the A+ hours. Once we have that, we can go ahead and calculate the Kruskal-Wallis H statistic. Here is the equation, a bit intense, but you break it down step by step. N is the total number, capital N is the total number of observations. K is the total number of groups. R is the sum of ranks for a particular group. And lowercase n is just the number of observations for that group. So first we calculate this one, which is equivalent to the rank variance. Is 12 divided by n times n plus 1. If you calculate that, you get 0.05. And then you calculate the this part of the equation, which is just r squared. So the sum of ranks for each group squared divided by the sample size, and you calculate that for each of those samples, and then you sum it, because that's what the equation is asking you to do. And then because the Kruskal-Wallis H statistic follows a chi-square distribution, you kind of have to scale it to the chi-square distribution using this 3 times n plus 1, right? So 3 times n plus 1, which is 16, gives you 48, right? And then once you have that, you get 48 minus 48.85 minus 48 gives you an H value of 0.85. Now we have to compare this value to a critical H value, and we'll talk more about this next week. But the H statistic follows a chi-square distribution. And so we'll talk more about the chi-square distribution in a little bit, but essentially the chi-square distribution, just like the F distribution, just like the T distribution, changes shapes depending on the degrees of freedom. The degrees of freedom is just K minus 1, which is the number of group minus 1. So here we have 2 degrees of freedom. So for example, this is a chi-square table. You have 2 degrees of freedom and an alpha of 0.05, but you can choose your own alpha. Gives us a critical H value of 5.99. So we compare that value. Because our observed value is less extreme than our critical value, we fail to reject the null hypothesis. So we report it by saying something to the effect of a Kruskal-Wallis test was conducted to evaluate whether there was a significant difference in well-being scores among 3 groups of sleep duration: more than 8 hours, 6 to 8 hours, and less than 6 hours per night. The results of the test indicated that there was no statistically significant difference in well-being scores among the 3 sleep groups. You give the H value, the degrees of freedom, as well as the H statistic, and P greater than 0.05 because our P value is greater than 0.05. And that's how easy it is to do this by hand. Not that complicated until you get many, many observations. But in this part of the lab, actually I want to focus on how do we do this in R. So we'll just retake our lab. So you can open this lab 8 document that we have here, and I'm gonna want to follow up on the ANOVA that we conducted last time, because we conducted the ANOVA even though we failed the normality assumption. We did not meet it, right? So at that point, it would have been a good idea to just jump directly into the Kruskal-Wallis test, but of course, because I needed to teach you ANOVA, we did not do that. So let's get started. We're gonna load our packages in our dlooker package, the tidyverse, this FSA package. So you should install that package because that package is new. The FSA package conducts a dunce test for pairwise comparisons, and of course our effect size package. I'm going to set our working directory and load our data. And if you guys remember, I made a couple of changes to the data, making sure that all the variables had the right format, releveling some of those variables, making sure that we filter so we have only the sample for 2018 and only compares individuals' income on people that were actually working, so like had a full-time employment, and then we drop all missing observations on those two to create this subset 18 object. So, last Tuesday, we looked at the data and we saw right away that the data is not normally distributed. And even, when we tested for normality by group, we saw that, in fact, you can kind of see it here, that even when you split your data by group, income is not normally distributed. That's because income is never normally distributed, right? Income skews to the right pretty hard almost every time. In fact, every time. I've never seen income not being skewed to the right. And so this test, the results of this normality test here just, confirms what we see here. So given the skew that we have in our data, it is a good idea to not do an ANOVA and to conduct the Kruskal-Wallis test. And conducting the Kruskal-Wallis test is actually really simple. You just use the function Kruskal.test. You give it your dependent variable or numeric variable, the tilde, and the categorical variable or the grouping variable. Specify the data. You run it, and you'll see right away that the H statistic is essentially it gives you a chi-square value of 210 with 4 degrees of freedom, which is just 5 minus 1, and this p-value, which is 0.0016022, right? So it's essentially 0. This is less than an alpha of 0.01. So it's very, very tiny, very, very significant result. So great. So at least one of those groups significantly differs in the ranks from the others, right? This means two things. Just like it meant for ANOVA, it means two things. Number one, that we want to get a sense of the effect size, right? So for ANOVA, we use an eta square, but for a Kruskal-Wallis test, we're going to use a rank version of the eta square. So we're going to use rank underscore eta square. You give it the equation that we use above. You run that, and you see that the rank eta square is 0.21, right? So 21% of the variance in rank scores is attributed to the independent variable. So 21% of the variation in rank scores is attributed to variations or to the independent variable, right? So if you look at the HTML document, there is some sort of criteria as to decide what is a small effect, medium effect, large effect. So anything above 14% is a large effect. So 21%. So education has quite a large effect on income, not surprisingly. The second thing that we must do after we determine the effect size is that we need to do a post hoc test to determine which groups are significantly different from the others. Which groups are significantly different from the others? Last time we used the Tukey test if we met the assumption of homogeneity of variance, or the pairwise comparisons test if it did not, right, meet the assumption of equality of variance. But because we're no longer dealing with differences between means, we have to go into the, again, rank world. So the most popular post hoc test for rank data, which we are kind of using this kind of rank version of ANOVA, is the done test. The package that has this function is this FSA package. Not really important what the package is because we're only going to use it for that one particular function. Make sure to install it. And so we use the done test. We give it the equation. We specify the data and the method of correction, because we're running a series of significance tests. We're going to use the most conservative one, which is Bonferroni. All right. So if you run that, you're going to get this, right? The comparison, the C value on that comparison, which corresponds to a T value almost, and the adjusted P value, which is what you want to look at. Essentially, these are all, tiny numbers, right? Way smaller than 0.05, 0.01. And in some cases, like this one, 0.001, right? Which are the three most commonly used alpha levels. So you can see that essentially they are statistically, almost all groups are statistically significantly different from each other, with the exception of one, which is this one right here, which is high school and junior college. There is no significant difference between these two groups. So we run our Kruskal-Wallis test, we ran our effect size, we run our post-hoc test. How do we put all of this together in a report that makes sense, without talking too much p-value less than this and alpha, reject and null, right? When you report this, it has to be in plain English, but also add those statistics there that are necessary for people who know their stats to be comfortable with what you're doing. So this is the way that I would report it. First, I like to start with my descriptive statistics to give my reader a sense of what's happening. So descriptive statistics revealed a clear trend in income levels across educational groups, with higher education associated with increased income. Median scores, because the moment that you go from parametric to non-parametric, do not report the mean, report the median, which is a non-parametric measure of center. Median scores for each educational level were as follows: so that's in high school. So this progression suggests that individuals with higher educational levels, higher educational attainment, tend to earn more. To determine if these differences were statistically significant, a Kruskal-Wallis test was conducted. Results indicated a significant effect of education on income. Give me the H value, the degrees of freedom, and the P less than whatever alpha you choose, because this P value that we calculated, which is right here, is so tiny. It's always good to just choose the lowest alpha possible that you pass, and that's why I said P less than 0.001, suggesting that income varies across educational levels. The effect size, calculated as rank-based eta squared, give me the eta squared, the 95% confidence interval, reflects a large effect, with educational attainment explaining 21% of the variance in ranked income levels. Post-hoc pairwise comparisons using the Duns test with Bonferroni adjustment confirm significant differences between most educational groups. Specifically, bachelor's and graduate degrees differ significantly from all lower educational levels. High school and junior college did not show a significant difference, indicating similar income levels between these two groups. In summary, the results provide strong evidence that higher education is associated with higher income, with significant differences between most education levels, particularly between groups with substantial educational gaps. And, something like that, it doesn't have to be a one-to-one when you do it, but, you should, describe exactly what you are doing and what it means. Anyways, that is all for part 2. Thank you so much for watching. I'll see you in class.